Thank you. Thank you for coming on a Monday morning. I hope you had a nice weekend and that you didn't do physics and instead you enjoyed the town. Life is short after all. So after the last 3 lectures and the orgy of algebra, I think I'm going to stop here and use the last 2 lectures to discuss a bit quantum field theory aspects of the problem, and in particular conformal field theory. But we will go back to algebra very soon. So now when you have a model like my darling loop models, there are 3 basic questions you can ask yourself once you've understood that there are critical phases and that you can expect some sort of universality within these phases. These are 2 aspects that are believed to be true much more generally, of course. The main questions you can ask yourself are, what are the critical exponents? For instance, the other day I mentioned the fractal dimension of the clusters of up spins in an Ising model at critical temperature and in the high temperature phase. These are examples of what we call critical exponents. Then moving on a bit in the direction of quantum field theory per se, you can ask yourself, what is the Hilbert space? And I use Hilbert in quotation marks because another point I have emphasized already is that these theories are not unitary. And I think Hilbert proper would require the existence of some non-degenerate positive definite scalar product, which will not be the case here. But what is the Hilbert space of the quantum field theory, which is a fancy way of asking what are all the observables what does the symmetry mean when the parameters are real or complex? For instance, what does ON or UN mean when n belongs to C? What are the OPEs? OPEs here stands for operator product algebra, one of the basic tools to solve quantum field theories per se. And finally, the answer really to what we call solving a quantum field theory, what are the correlation functions? Example, you give yourself 5 points and you ask yourself what is the probability that these 5 points all belong to the same cluster of up spins in the Ising model, say. This is, in fact, an extremely difficult question whose answer is now known somewhat, but requires an amount of technicality that is definitely very heavy. All right, so I want to consider some of these questions and use them as an excuse to tell you about conformal field theory. I warned you my lectures would not be pedagogical very much. My goal is rather to go over a set of topics. I see some people laughing. That's the way. But I think there'll be plenty of pedagogy later on. Now I am very reassured because Fabian is in the room, so I can trust that you'll get things very pedagogically explained later on. Some of those things maybe. All right. So let's try to answer all these questions, and there are various strategies to answer these questions. One of them would be purely algebraic, and it would consist in, once we have identified the central role played by these lattice algebras, use appropriate representations of the algebra and do some calculations using the beta ansatz, because it turns out that in some of these representations you can indeed use the beta ansatz. This is a very difficult route that stops anyway very quickly. Pretty much after step 1, we would be stuck because it still remains extremely hard to calculate correlation functions using the beta ansatz. So we're going to use other strategies inspired by quantum field theory, and some of these strategies may look like magic, and well, it takes time to justify the results, but you can trust me that in the end we're getting something that's correct. So let's focus first about the critical exponent. Yes?
What is the distinction between correlation functions and OPEs? Can you correlation?
Well, so what we call OPEs are, let's say, if we're having two observables in our quantum field theory, the general concept of OPE consists in asking oneself, if we look at these two observables from very far away, they will look like, hopefully, and that's not a trivial question, they will look hopefully like some sort of sums of local observables, roughly centered in the middle, times some coefficients, right? And the question of the OPEs is the question of what are the operators appearing on the right-hand side. The question of the correlation function is, of course, if we know the correlation function, we know the OPE, but the converse is not true, right? The correlation function would be really find a beast like this as a function of R1, R2, R3, R4, and that's more difficult, okay? And in fact, it so turns out that for technical reasons, it is easier to calculate this correlation function using the bootstrap and then use the results to deduce the OPs rather than the other way around. All right, so what are the critical exponents? Let's attack this question first using an extraordinarily simple construction that's very inspiring, but unfortunately stops short of solving the problem completely, which is called often a Coulomb gas mapping. So let me try to explain this first. Let's go back to our, so remember, all the models we're interested in have partition functions of the type sum over k to the b n to the l, where b is the number of bonds and n is the number of loops. So that's the general construction, general type of model we're having, which therefore at criticality or below the critical point gives us an ensemble of loops. So we're having loops within loops like this. And in order to make progress on this problem, the first thing we can do is try to make the Boltzmann weight local. Because, like I emphasized before, these weights, as they are defined, are non-local in the sense that in order to know that two pieces belong to the same loop, I need to have some non-trivial information. Right? In order to know that there's a road going from Rome to Florence, I need to look on the map and make sure there is one. Of course, all the roads go to Rome, so that's not a good example, but still. So how to make this problem local is in fact extremely easy, although it's also very subtle. But the trick in the plane, and there's a lot of caveats here, the trick to make the model local in the plane consists first in orienting the loops. So this is sometimes confusing because I mentioned that one of the loop models, the model associated with the Potts model, is in fact naturally an orientable model. And I'm going to orient the loops, but it's going to be a different philosophy. Each loop will be oriented in two possible directions, and I'm going to sum over the orientations. So allow me for a minute to orient each loop, just for the heck of it. I can of course do that, and if I decide to sum over orientations, I can replace my model of unoriented loops by a model of loops where each loop has two possible orientations. I can always do that, but the two possible orientations spoil the Boltzmann weight. I wanted a weight n per loop, and now what do? I have two orientations. What do I do with my weight n? Well, there's another trick, which consists in associate to every right or left turn, a concept that's fully well defined on the plane, a complex weight e to the plus or minus I something. And I have to think a little bit about what the something should be. This something should depend on the lattice. So for instance, if I look at the honeycomb lattice, I hope you all see that for every loop on that lattice, here's one, the number of left minus the number of right turns will always be equal to plus or minus 6. This is something that's inherent to the topology of the lattice. In order to close a loop, since I'm only allowed turns of plus or minus 120 degrees 2 pi over 3 at every step, in the end, in order to close the loop, I need that the number of left minus the number of right turns equal to plus or minus 6. So left minus right in absolute value is equal to 6. Do you all see that? Okay. So if I give for the model on the honeycomb lattice a weight e to the plus or minus I alpha, and if I choose that 2 cosine 6 alpha is equal to n, I will have ensured that every loop gets the correct fugacity n. And I can replace the model I had, a model of non-local Boltzmann weights, by now a totally local model where I demand that on every edge I have nothing or an oriented edge. I demand that the edges conserve the current, which is a local condition, and I give a weight plus or minus e to the I alpha to the left or right turns. This way I've made my model into a local model. It's local, but the Boltzmann weights are complex. So this is the first price we have to pay, and it is the origin of all the difficulties. If we had a model that's really local with positive Boltzmann weights, there are general theorems that would tell us that the quantum field theory is at the critical point a unitary conformal field theory, and we would have a lot of tools at our disposal. The problem is that it's not the case. The only way to make the theory local involves complex Boltzmann weights, and because of that, the quantum field theory is not unitary. So I use the word quantum field theory, even though right now we are really doing statistical mechanics in 2 dimensions, because I am kind of assuming that you all know that we can go from critical phenomena in 2 classical dimensions to quantum phenomena in 1 plus 1 dimensions, quantum phenomena that are moreover relativistically invariant if we have a critical point in 2 dimensions. Now this may be obvious to some of you, not to others, so I will discuss this a little bit more later. For now, if the word quantum field theory traumatizes you, in particular the word quantum, we haven't seen H bar anywhere yet. We'll talk about it later, okay? So think of it just as a field theory otherwise. All right, so this is the trick number 1, and now it becomes a little bit technical because, as you can guess, if you were doing things on a different lattice, the rule to produce the weight of the loops would be a little bit different. So even though I started by thinking about the hexagonal lattice, you can see that this kind of construction is general. And I would like now following the philosophy I've had so far, hang on, I would like to discuss things specifically for the Potts model where the loops live on the square lattice instead. Yes? Because every time, okay, sorry, I thought it was obvious, maybe it's not. So look at this loop. What is the weight it's getting from the corner weights? It's e to the, you got it? Everybody got it? If I do this, I get e to the 6i alpha, but I can also orient it the other way. So in the end, this is what I get. Okay? Right? Good. Okay, so now let's focus specifically. Like I said, things depend a bit on the lattice, although the general conclusions do not. But I want to focus specifically on the case of the Potts model because it will allow me to make some smart remarks about the 6-vertex model. So now let's focus specifically on the Potts model. So remember, I use n generally to denote the fugacity of the loops. And we have seen already that in the case of the Potts model, we get loops whose fugacity is expressed in terms of the number of variables of the Potts model as square root of q. And remember, we have this nice construction where we're having clusters in the Potts model with some edges belonging to the clusters, others not. So now maybe I'm shading the edges that are not occupied, just to be more explicit. And then what we did, we had this bizarre construction where we had a surrounding lattice, as we called it, whose vertices were centered on the edges of the original lattice, so it should be squares. I'm not drawing very well. I guess I should have done a better job here. Okay. So this is the kind of lattice we get, the surrounding lattice. And then on that surrounding lattice, remember, we drew our loops so that whenever we take a bond on the original lattice, the loops avoid the corresponding edge, while whenever there is no bond on the original lattice, the loops cross the edge. So for instance here, now I'm not going to draw the surrounding lattice anymore because it's really annoying. I'm going to have something like this, something like this, something like this, and maybe you can ask for yourself what it is you have, although it's kind of obvious. Okay. So this is what we would have with periodic boundary conditions. I have one loop here. I have this guy that's coming out, going like this one, and this one that's not contractible. Okay, that's what I would have with periodic boundary conditions. But be very careful with boundary conditions. All our discussion so far will be in the plane. Anyway, I'm only going to focus locally, and the first point to make is that now on this square lattice, the number of left minus the number of right turns is not equal to 6, it is equal to what? 4, thank you. So now the rule is that we want square root of q is 2 cosine 4 times something. So now the usual convention denotes this number by gamma. It is kind of standard now. So q belonging to 0, 4 means we're going to take gamma between 0 and pi over 2. And then we're going to associate to left and right terms the weights e to the minus or plus e to the I gamma over 4. If we do this, every loop on the plane gets a weight 2 cosine gamma. You already see here that topology is going to come and hit us in the back, bite us in behind, something, because a loop like this loop, which is not contractible, has as many left as right turns. So our rule doesn't work for loops like this. We'll have to do something. And the something is what makes the problem extremely difficult, actually. But for now, let's not worry about this. Let's just observe this fact that we can do the construction on the square lattice with the same rules. And now a remark about the 6-vertex model. I don't really have to do this, but I think it's useful because many of you may have heard of it a little bit. What is the 6-vertex model and what does it have to do with the story? Well, the idea is the following. If you look at one of the edges of the original lattice, you can. Okay, let's try to do it differently. Let's look at a configuration with our oriented loops. So here, for instance, is a configuration where here I have an oriented loop like this and here one like this, just as an example. The idea is now to observe that we can always glue together the two pieces of the loop at the point where they avoid each other. And if we do this, what we're going to obtain is a vertex that looks like this. Okay? So in fact, a little bit of thinking shows that we can have in the rules of the game, we can have 6 possible vertices. We can have this one, this one, this one, this one. Then we can have this one, that one, that one. It's always hard on the blackboard to make sure you don't miss anything. And then we're going to have this guy, and we're going to have this guy. Okay, these are the 6 possible vertices. Why 6? Because, of course, the rules of the game are that we orient the loops in a way that is consistent. Therefore, current is conserved, where by current I mean the number of arrows going in is equal to the number of arrows going out. So this is the 6 possible vertices we obtain. And more to the point, we can really have a complete map between the vertex configurations and the loop configurations. Only what happens is that sometimes one vertex configuration may correspond to 2 loops. So let me draw this one here, because I want to draw something below. Let's see what these vertices can come from the point of view of loops. Well, from the point of view of loops, this guy can only come from this, because I would need to have current conservation. This guy can only come from that. This one can only come from this. This one can only come from that. Okay. But these are more interesting, because this one can come from this or that. And this one can come from this or that. Okay, so the 6-vertex model can in fact be mapped onto the loop model when you understand this feature. And you can even calculate the weights of the vertices, because what are the weights? In the loop model associated with the Potts model, all the edges are occupied. So there's no question of weight per edge. It's like a very, very packed limit of the general loop model where we would have some vacancies. All the weights come from the turns. Here I have a left turn and a right turn, so this has weight 1. Here I have a right turn and a left turn, weight 1. Here I have right, left 1, weight 1. Only these 2 have interesting weights. This one has 2 left turn, this one has 2 right turn, this one has 2 right turn, this one has 2 left turn. So both of them have weight 2 cosine gamma over 2. And it's an easy exercise to convince yourself that the weights that the partition function of the vertex model is essentially up to boundary effects that I'm not going to discuss for now, the same as the partition function of the loop model. So the reason I mention this is because there are always a few aficionados of Yang-Baxter equation in this room, I hope. And this is the connection with the six-vertex model that can be extremely profitable. It is the parallel of something I discussed in the discussion session on Friday, that is the representation of the Temple-Lib algebra in the XXZ spin chain. All these things are connected. But if you are not particularly enamored with integrable systems, you can forget this remark about the six-vertex model. It's just to indicate a route to calculate things using the beta ansatz, but I'm not going to do this. Okay? I'm going to focus on my very naive ideas of giving to left and right loops, left and right turns in loops, phases, and I'm going to try to carry on from there. Okay? So, so we've made the model local but non-unitary. Now what? Now what? Well, now comes the big hypothesis. So, okay, first, now look at the oriented loops. Okay, so now we have our loops. Again, I'm doing some abstract construction, but when it comes to details, I'll probably go back to my model associated with the Potts model. Now look at the oriented loops and imagine that this loop represents domain walls. Okay, interpret the loops as domain walls. Domain walls for what? Domain walls for a model of interface. It's called sometimes a solid on solid model. Because we're thinking of an interface that is characterized by only one quantity. So it's like when you go to the Italian restaurant and you have the oil and the vinegar bottle. Don't do it, but you could amuse yourself by pouring the vinegar into the oil bottle, for instance. Don't do it. And see what happens. And what happens, of course, is you're going to have an interface with, in this case, the vinegar on top and the oil at the bottom, and that interface will not be perfectly flat. It will be characterized by height, right? Of course, next you may shake the bottle, and right before they kick you out of the restaurant, observe, and you will see that then you will have bubbles of the vinegar inside the oil, because the interface between the two media will be much more complicated in that case, right? We are not worried about this. We only want the nice interface entirely defined by just one coordinate. This is what we are thinking of here. So, to carry on, what we're going to decide to build our interface, let me just make sure I have my notation straight. So that's a big phi, I think. We're going to decide that we're going to define this interface, the height of this interface, the height of the interface in the bottle of olive oil, if you wish. We're going to define it such that when two heights are separated by an arrow going up, I decided that, oh gosh, should have made a note of it, sorry. Okay. Decided that this one, we're going to decide that this one is equal to that one plus pi. It's going to be our convention. Okay, so if we fix the height at infinity, and once again you see that the boundaries are going to bother us, because if we were on a torus there wouldn't be any infinity, but assume we are on the plane, we're going to fix the height at infinity to be 0, and then we can define all the heights recursively by looking simply at the arrows we encounter. So let's translate our loop configuration into a height configuration. These guys here are a domain that's to the left of the domain at 0, so these heights are equal to pi. Now this arrow goes like this, so this high is equal to 2 pi. This one goes like this, so again inside I have pi. Similarly, here I had pi, so I have 2 pi, here I have 0, and here I must have 2 pi, something like this, okay? So I've transformed my set of loops into a set of domains. So this is a domain, this is another domain, this is another domain. Okay, this is a domain, this is another domain, okay? And of course, outside, I also have one big domain, and so on and so forth, okay? So if I define the heights technically on the dual of the lattice that supports the loops, it will be the triangular lattice for if the loops live on the honeycomb lattice. It will be yet another square lattice if the loops live on the square lattice as I drew up there. I have a one-to-one correspondence between the heights and the configurations of oriented loops. Okay? So this is a nice step. There's a one-to-one correspondence between, once again, heights and by heights I mean the values of phi and oriented loops. All right, very good. You see also that you see also that it's very good that the loops don't intersect each other. If I had something like this, my construction would completely break down because I would say, okay, this height here will be phi, then the one to the left would be phi plus pi, the one here should be phi plus 2 pi, the one here should be phi plus 3 pi, if I count like this. But on the other hand, now we would having two heights differing by 3 pi, while they should be differing only by pi, since the rule was that heights on the left of the arrow should differ from the ones on the right by pi. So I would encounter a contradiction. We cannot transform the model where loops are crossing into a solid-on-solid model, and that's actually a very important observation. I could not map onto a solid-on-solid model. Now, what do we gain by mapping onto a solid-on-solid model? Well, now we need an act of faith. There will be a claim that I'm not going to justify except by the fact that the consequences are verified. Claim up to subtle effects, and that of course is really a very lousy way of stating things, but I have to go over the subtle effects later on. The dynamics of phi is described at large distances by decorations, and once again this is a lousy statement, but that's what I can do for now, of a free bosonic field. And now I can stop. Fabian comes and gives the end of the lectures. Okay. A free bosonic field. Okay, so what is a free bosonic field first? And how do we know that this is true? So what we mean by this is we're going to be able to calculate some properties of the model of loops by using decorations of essentially a free boson. This should not be a surprise, I guess, a posteriori, for those of you who know in particular aspects of solid-state physics. you know that there is a lot of interacting quantum systems in 1+1 dimension, which are related with classical interacting systems in 2 dimensions, whose interactions can be formulated in terms of bosons and so on and so forth. So maybe it is not such a surprise. Nonetheless, it is kind of striking that this will be true, and it's not totally obvious, so there will be many subtle effects, point number 1. And point number 2, there will be the decorations of the free boson, which are also subtle things to take into account. But what I'm saying morally is that the dynamics of phi at large distances is pretty much described by simply a Gaussian action. So now let me discuss what I mean by Gaussian action and how it connects with the claim related with the heights. So what is the Gaussian action? What is the so-called free boson CFT? So no conformal field theory yet, but let's start throwing the word around. It will look good. So this is a model whose action is, so I'm going to be very careful with notations. So this is a phi without the hat and the shoes. This is a fat with high and shoes. Don't confuse the two. There will be a normalization issue. But basically, the free boson is a model whose action is this, which means, for instance, that the partition function is defined as the integral over all the configurations of e to the minus s. Okay? Looks familiar enough? You all know about path integrals, you all know about actions? Okay. So, like all path integrals, it's going to involve subtleties. In fact, in a very precise sense, this theory is extremely complicated, but naively, at least, it looks very simple because it is Gaussian, right? In a Gaussian theory, we in principle will know how to calculate everything. So what I am saying is that the dynamics of the heights in the loop model at long distance is described, by observables in this theory. And because it is a free theory, free or Gaussian, I am going to be able to calculate things and compare them with, for instance, numerical simulations, etc., for the loop model. Of course, the claim I'm making is absolutely staggering. It is not clear at all that the dynamics I have on the lattice maps onto this simple model, but I am making this claim, and it can be checked in many different ways. But what I want to do is use the claim, derive properties, and then a posteriori make sure that these properties are correct. So I'm not going to justify this much, except by saying that it's been checked by many very serious people over the years. And what you can do, for instance, is really do a real space renormalization on the initial model and see what kind of fixed point you get, and definitely this seems to be true. Up to a question of normalization. Sorry, yes, I'm going to get closer because I know you don't speak loud. How do I what? Sorry? Yes. Does it need to be local? What do you mean by this? Well, the way I defined it is it's defined non-locally, but in the end it is a local observable. Let me comment on this later on. I think some of you may also know that free bosons are compactified, and I haven't talked about this aspect yet either. I will talk about it in 2 minutes. Okay. So for now, maybe the best is to forget the introduction and focus on this a little bit, because I want to discuss the free boson a little bit as a theory, irrespective of where it comes from, and then we will go back to where it came from in this lecture. So this theory is particularly nice because it doesn't even require a dimension full coupling. Phi is dimensionless. This is dimension of length square. Gradient means, by the way, in case it's not clear, dx phi square plus dy phi square. This term has dimension length to the minus 2, so the whole thing is dimensionless, right? So this theory is a very nice theory. It is the only theory we know how to solve. I think it's Sid Coleman who used to say, the career of a theoretical physicist consists in solving the free boson theory in more and more sophisticated ways. That's exactly what I'm doing here. That's the end of my career. I'm solving it in a really very, very sophisticated way. All right, so this is, however, a subtle theory. It is a subtle theory because, like every quantum field theory, a lot of stuff is hidden under the carpet. In particular, the meaning of the measure here. And we'll have to face some of these minor difficulties sooner or later. But to start, let us give, so what is the simplest thing to give is the so-called propagator, which is the 2-point function. Let me make sure I keep using good notations. Okay, so for now I'm going to use R to denote the vector with coordinates x and y, although very soon I'm going to move to conformal field theory notations, but not for now. So phi of R1, R1 bar, phi of R1, phi of R2. This object is easy to calculate. I'm not calculating the partition function. This thing is easy to calculate because we're having a Gaussian integral. So you can calculate the 2-point function in a Gaussian theory simply by calculating the inverse of the matrix that defines the action. And the net result is that, of course, this thing is infinite. This thing is infinite for a variety of reasons that are all extremely annoying. First of all, when we write an integral like this, it should be clear that the partition function is going to be infinite because the action depends only on the gradient of phi, but phi itself has not been defined so far up to an additive constant. So I have a zero mode that makes this partition function, of course, infinite, okay? Infinite because of zero mode. Okay, so very often it is actually customary to define the partition function as the integral over all the modes but the zero mode, which may coincide essentially with fixing the heights at infinity. That's not a surprise. We've seen when we defined our equivalence between loops and phi that we needed to fix the height at infinity in order to define the heights everywhere else. So we're getting at the end what we were expecting. But it's still infinite even if we kill the zero mode, because like every quantum field theory, to be properly defined, it needs a cutoff. Okay? Needs a cutoff to be properly defined. And now we're entering a world of pain, if I may cite from, okay, nobody's laughing, yeah, you just don't know the references. If I say we're entering a world of pain, nobody knows what I mean? No, Big Lebowski. What are you guys doing over the weekend, like physics? All right, so need a cutoff to be properly defined, and the best way to have a cutoff, in fact, I guess I come from a school where people do not even believe a quantum field theory exists if there is no underlying lattice, but that's a philosophical question mostly. So we can have the cutoff naturally by defining the theory on the lattice initially. Lattice, just like what we had earlier. So what you do if you want to define this kind of theory properly is you need to define phi on the lattice. So phi of R becomes phi of, let's call the coordinates I and j, IA and GA, where this would be the cutoff, okay? And then you need to define dx phi, for instance, as phi of I plus 1a JA minus phi of IA JA, something like this, etc. Right? If you do this, it's totally straightforward, and you end up with the propagator, as it's called, of the free boson with an explicit cutoff dependency. So that dependency can be expressed. I'm going now to write this G. I'm going to call it G lattice because I imply that I'm having an underlying lattice. It depends on the 2 points. And what's really important is that G lattice goes like, and now I need to do things well, minus 1 over 2 pi log of, and now this is where the devil comes in, R over L, when A is much smaller than R, much smaller than L, and G lattice goes like minus 1 over 2 pi, so G lattice of 0, minus 1 over 2 pi log of A over L. So it so happens when you do the calculation that not only do you need a UV cutoff, but you also need an infrared cutoff in this theory. This is just the way it is. If you put the theory on an infinite system, the propagators will be infinite. So not only do you need a UV cutoff, you also need an infrared cutoff. And the reason is that whenever you deal with this free boson, everything comes out as involving integrals like RdR over R square. And this kind of integral is particularly unpleasant because it has divergences both at R small and at R large. And that ultimately is why you're having to worry about not only an infrared cutoff, but also a UV cutoff. This, sorry? So UV cutoff means short distance cutoff. And short distance is A, UV short distance, okay? Infrared means long distance. So that's the size of the system. There's a lot of physics here, by the way. I alluded to the Mermin-Wagner theorem last time. Ultimately, the Mermin-Wagner theorem comes from the encountering of this kind of integrals and the fact that if you have a free boson, which is a good description of the Goldstone modes, if you have a continuous symmetry spontaneously broken, is that things at large distance tend to have fluctuations of the order of the log of the size of the system. So that's why continuous symmetry cannot be spontaneously broken, and more to the point here, that's why you encounter this L. So I'm not going to derive this. Let me just tell you what it is, because anyway it's not going to be too important for us, but it is a very important point to remember, because in particular our cousins, the string theorists, handle the free boson in a way that's a bit cavalier sometimes. And I think we have to be very careful with this beast. So the way to be careful is to a priori keep these 2 cutoffs. In other words, the theory can only be properly defined, I claim, if first of all we have a short distance quantity A, and second of all we have a large distance quantity L. It's okay for statistical mechanics, right? We don't care. We know we have these things, but this might create problems later. All right, so this, again, this is true when the distance is much larger than A, so it becomes nice. And this is true at very, very small distances. So you see in particular that if the cutoff, the UV cutoff is sent to 0, all the correlation function at origin becomes infinite. which is something that will have very big consequences very shortly. So now let's carry on a little bit with our free boson. But let me say that these features make the free boson as a conformal field theory a little bit difficult to handle. Okay, so the propagator is the first step. The second step, once you have the propagator, is to use what's called Wick's theorem, which I assume also everybody knows, but I'm going to remind you what it is in this context. All I'm going to use is the following, is that the average of e to the some quantity, well, okay, how to state it? Well, okay, let's write it like this. Alpha I phi of Ri is equal to exponential of 1/2 average of sum of alpha I phi of Ri square. Okay? Which, let's illustrate things immediately. Average of exponential I, so now I'm putting an I, how did I call this? Beta. Beta 1 phi of R1 e to the I beta 2 phi of R2. Okay, this average, I use my Wick's theorem. Of course, this is the same as the exponential of I beta 1 phi 1 plus beta 2 phi of R2. And then there's exponential of 1/2 average of beta 1 phi of R1 plus beta 2 phi of R2 square. Okay, that's the theorem. And Wick's theorem is more generally telling you that the average of the exponential is essentially the exponential of the average of the square, which is a property that comes only in Gaussian integrals. You may know, by the way, Wick's theorem in another guise by the fact that the correlation function of a product of a bunch of phis is the sum over contractions. That's how everybody knows it, I guess. So equivalently, phi of, so now let me use 1, 2, 3, 4 instead of R1, R2, R3, R4. You would have that this is the sum over pairwise contractions, right? So 1, 2, 3, 4, we would have this, plus we would have this, plus we would have something like this, okay? Where 1, 2 means phi of R1, phi of R2, and so on, right? This is the way most of you know it, okay? So if you use this kind of thing and plug it into the exponential, you get the theorem in the way I want to use it, which is this formula. All right, so let's now observe that this average of phi of R1, phi of R2 is not particularly nice because it's a logarithm. Remember, we didn't want logarithms, we wanted power laws. I started these lectures by saying the correlation functions decay as power laws. So luckily, we can get power laws if we look at exponentials of the field. So let us now calculate in our free boson theory this correlation function by using Wick's theorem. Okay, so this is, by the way, because there was an I, this is now -1. Alpha is I beta, so there is a minus. So let's calculate it using the theorem explicitly. This is exponential -1/2 times some horrible stuff, what does it have? It has beta 1 square average of phi of R1 square plus beta 2 square average of phi of R2 square plus 2 beta 1 beta 2 phi of R1 phi of R2. Okay? Well, let's now replace with, so remember G was the 2-point function of phi regularized on the lattice. So I can use my two formulas up there. I'm going to assume that R1 minus R2 is much larger than A and much smaller than L. I get exponential minus 1/2 times. So average of phi square of R1 and average of phi square of R2, they're the same, right? The system is translation invariant. So I get beta 1 square plus beta 2 square times average of phi square at the same point, which I regularize with my cutoff, minus 1 over 2 pi log of A over L. Okay, a horrible thing that depends on A and on L. And then I have the plus 2 beta 1 beta 2 times phi of R1 phi of R2, which is minus 1 over 2 pi log of R1 minus R2 over L. Okay? Really a very unwieldy expression if you ever saw one. Let's try to make it a little bit nicer by rewriting it as exponential. So, of course you will understand I must put a bracket here also, but I'm getting a little tired of it now. 1, 2, 3 levels of parentheses. Exponential minus 1/2, and then I have, so I'm gonna add and subtract beta 1, beta 2. So I want to replace my beta 1 square plus beta 2 square by beta 1 plus beta 2 square times minus 1 over 2 pi log A over L. And then I have the other term, which I'm going to write minus beta 1 beta 2 over pi log of R1 2 over L. And then here up there I introduced a term I don't want, which is minus beta 1 beta 2 over pi log of A over L. So I need to add beta 1 beta 2 over pi log A over L. Okay? Hopefully I haven't made a mistake. And then this is okay. So now we can put everything together. I get A over L to the beta 1 plus beta 2 square over 4 pi. And then I get, so what else do I get? I get exponential, let's make sure we don't make a mistake, so let's calculate the intermediate term, minus minus is plus, beta 1 beta 2 over 2 pi, and then I have log of R1 2 over L, but because I factored out minus beta 1 beta 2 over pi, I have log of R1 2 over L minus log of A over L, which is log of L over A. Okay, so this is what I get. So finally, this horror thing was pi. So finally, I get, and then I'll stop after this, beta 1 plus beta 2 square over 4 pi. And then the L's disappear, oh joy, and I get R1 2 over A to the beta 1 beta 2 over 2 pi. Okay? The very laborious calculation, but I think it's quite useful. Why is it useful? Because we now see some obvious facts. We now obviously see that if beta 1 plus beta 2 is non-zero, this two-point function vanishes when L goes to infinity. So that's a constraint that in a way imposes charge neutrality in the system. This is where the word Coulomb gas originates from, at least partly. Of course, the other reason it comes in is because the propagator is like solution of the Laplace equation in 2D electrodynamics, electrostatics. But for us, what matters is the two-point function equals 0 if beta 1 plus beta 2 is different from 0 as L goes to infinity. So if I want to consider a large system, the correlation functions of, in fact, it's true for any product of exponentials, and that's why we call the coefficients the charges. Beta 1 is often referred to as a charge. The two-point function, the endpoint function, vanishes if the sum of the charges is not equal to 0. Okay? And if it is equal to 0, then we get a result that's very pleasant because it doesn't depend on L. And it was really annoying to have the dependency on the volume. You've never heard of a nice quantum field theory where things depend not only on the UV cutoff, but also on the infrared cutoff. I mean, it may happen, but it's not nice if you want to define a local theory. But luckily, if beta 1 plus beta 2 equals 0, and I'm going to set beta 1 equals beta, beta 2 equals minus beta, then we have equal A over R12 to the beta square over 2 pi. So now that's very nice because it doesn't depend on the size of the system. So welcome to critical exponents. This is the first critical exponent that we will encounter. And we see that we have a nice correlation function that is really scale invariant, and it involves a dimension. So very often we will say that the dimension of e to the I beta phi, although here I'm getting a little bit ahead of myself, is d beta equals beta square over 4 pi. That's the convention. But the point is we get a correlation function that doesn't depend on the size of the system. It, however, still depends on the cutoff. But that shouldn't be a surprise because you've started with a field phi that's dimensionless. You're taking the average of e to the I beta phi, which is a dimensionless quantity. How could you expect in the end not to get something that's dimensionless, right? So far we are on safe grounds, dimensionless, dimensionless, and crucial point, when the sum of the charges is 0, the powers of L disappear, and all we have is something that depends only on the cutoff. So this is, if you wish, a baby quantum field theory. This is a baby conformal field theory. We are not quite there yet, but almost. So after the break, I'll explain how to get rid of A, and then what it has to do with conformal invariance. And after this, we will come back to our loop model and calculate some exponents. Okay? Now let's have a break, and questions will come at the break. Thanks. So first of all, I have to apologize. I made a mistake pointed out by several of you. Thank you. When I said, I forgot what I said, anyway, it was dumb. When I had two loops crossing, I said something like the heights cannot be consistently defined, but that wasn't true. I just made a mistake in my calculation. the heights are perfectly well defined around a vertex where the current is conserved. It is actually another way of saying that the current is conserved, is to say that the heights can be perfectly defined. So I was wrong. It is not because of this that we cannot have self-intersecting loops. The reason we cannot have self-intersecting loops is because if we have a loop that's self-intersecting, it in fact turns out to have as many rotations in one direction as rotations in another direction. This loop, for instance, turns to the right 6 times and then turns to the left 6 times again. So we could not give such loops the weight n by the trick of associating complex weights to local terms. And that's why it is, in a sense, a different universality class. Even though I will argue later on that in the dilute phase crossings are irrelevant, but nonetheless, for now, we don't want to think about crossings. Okay? Thank you for pointing it out. So, where was I? Yes, this thing up there. So it is customary to deal with correlators that don't involve the cutoff. And there are two ways to think of this. One is to say, oh, I'm going to count distances in units of the cutoff. But that's extremely dangerous because when you want to make transformations, like scale transformation or conformal transformations, you have to worry about what you want to do with the cutoff. So a slightly better way to do this, even though I don't think it buys you much in the end, is to deal with what's called multiplicatively renormalized operators. Now, in general, exponentials of the field are called vertex operator. And what we do is we're going to define e to the I beta phi with double dots like this. We're going to define it as e to the minus beta square over 4 pi times e to the I beta phi. Okay? This is going to be a definition. There will be a lot to say about this. I trust Fabian will discuss it in detail. Another way of getting rid of the cutoff would be to prevent self-contractions. This is what these dots represent. For those of you who know a bit about quantum field theory, this may be a more natural way to think of it. I'm not going to worry too much about it, except that when we have to talk about conformal invariance, the cutoff is going to come back and demand attention. But for the time being, I'm simply going to assume I'm getting rid of A by renormalizing my observables, so that instead of correlation functions of non-normal ordered operators, we're going to have correlation functions of normal ordered ones. So these double dots, again, they also mean normal order. So there's a lot to be said. It's really a whole class about bosonization, but none of it I really need. I just throw the word, so you'll see about it later on in the next lectures. But the point is that this is now 1 over R12 to the beta square over 2 pi. And now it is a dimensional full quantity, although you may decide to count distances in units of the lattice spacing, in which case these distances would be 1, but be careful with this kind of game. Okay, so that's very quick discussion of the free boson. I will go back to formal aspects of the free boson when I discuss conformal invariance. For now, I want to move on and see what I can say about my loop model. So jumping over a lot of obstacles, let's remember that we have argued that the loop model can be transformed into a height model for which the dynamics should be a free boson. Since we know how to calculate things for the free boson, well, at least some of them, we should be able to calculate things for the loop model. This is what I want to do now. Okay, so free boson and loop model. So first of all, there's an issue of normalization. In string theory, people like to normalize the free boson using a certain normalization, which is pretty much the one I used. That's also the one used by Coleman in the old days and so on. It's chosen essentially because when you go to the Hamiltonian formalism, you have a nice Hamiltonian. In statistical mechanics, it so turns out that people like to have a slightly different normalization. So I am going to have to do this, unfortunately. So we're going first of all to change normalizations. So that we're going to write the action a bit differently. Okay? So all I've done is renormalized by introducing a phi without the top and the bottom, right? And the relationship with what I had earlier is that big phi is square root of g over 2 pi times little phi. Okay. Okay? That's not really a very big price to pay. And now the question is, so this phi, I've been hopefully careful, is the same as the one I used earlier. This is the phi for which I had decided that heights on both sides of an oriented arrow are separated by pi. So this pi is a convention in StatMech that comes from the ideas about the XY model and so on. That's why it's a pi. We think of phi sometimes as an angle. And one main question now, if we decide that on the lattice heights on either side of an oriented arrow are different by pi, the question now is what should be g, the coupling constant? This is really the main question. What should be the normalization of the action once we have decided that microscopically we have this conversion? So the question is, what is g for a given n, the weight of the loops, once we have agreed on a convention, once we had agreed on the convention that heights on the left and the right differ by pi. Okay, so this is the problem I have to solve. Once I will have solved the problem, I should be able to calculate some exponents. Alternatively, of course, I could decide to put all the normalization in the observables, and I could ask myself, for some given observable in the loop model, what is the beta I should use in the general calculations for the free boson in order to calculate the critical dimension? I'd rather not do that. I like to keep G in the action and have this fixed convention on the lattice. Okay? But every calculation can be translated immediately by just adopting this normalization. In particular, it's a straightforward exercise to see that, or maybe I should do it at the bottom here. So now e to the I e1 phi 1, meaning phi of 1, let's call it e minus ie phi of 2, normal ordered, is 1 over r1, 2 to the e square over g. Yeah, that must be correct. Yes. Yes. Okay, so easy translation. Okay, so now come the Maxwell demon, if I dare to call it this way. Unfortunately, the loop model does not really, strictly speaking, map onto a free boson. There are subtleties. Of course, you could expect subtleties. I haven't even justified that it maps onto a free boson, but the point is we control the subtleties to a certain extent. What are the subtleties? Well, let's remember that we decided to give loops going counterclockwise a weight e to the minus I gamma, and to loops going counterclockwise the weight e to the I gamma, right? This has been our convention. Now, let's imagine somewhere in the system we put an observable that I'm going to call e to the 2I e naught phi, and let's insert it at a particular point. Let's just take the origin, but the origin has nothing special. Let's just imagine that I insert this observable. What do I mean by inserting the observable? I mean that now I calculate sum over all the loop configurations of k to the b, n to the l, which I have traded for the weights of the turns. So I have e to I times some phase associated with the turns over the particular configuration. So this would be the partition function. And now I'm calculating not the partition function, but the average of this guy. Okay? So once again, this accounts for all the loop phases. And this is now the observable I have inserted. This kind of thing, of course, is just nothing else but this. Okay? So let me calculate the average of this guy. Well, it is a little bit diabolical, but let's observe that how do the weights of the oriented loops differ from when I have such a insertion and when I don't? So when I have no insertion, every loop gets a weight e to the plus or minus I gamma. I sum over, I get n per loop, I'm happy. Now if I have insertion, what happens? Well, now this loops gets a weight, remember, if I'm to the left of the arrows, phi is increased by pi. So I get e to the I E0. Now if the height here was, if the height on the right is just some number, let's call it phi right, in the domain around, I get e to the I E0 phi right plus pi, e to the minus I gamma. Yeah, okay, let me put it slightly differently. Let me once again fix the height at infinity to be 0. So phi equals 0 at infinity. Let's do it again, sorry. And let's see what this modification does. So once again, when I have no exponential, I have just the usual weights for the loops. If I add the exponential of t to the I0 phi of infinity, I have to ask myself, how does this affect the weight of the loops? So if I look at a path, let's assume for now that we have no loop surrounding this first loop. Then if I look at a path going from infinity to the point 0, what I see is I encounter each loop twice, once with orientation in one direction, with orientation in the other direction. And finally, I encounter the loop that surrounds the point. So because of the loop that surrounds the point, this contributes now an extra pi, because now the height in the center compared with the height at infinity has increased by pi. And then, because the loop is turning, it gets a weight e to the minus I gamma anyway. Okay? So because of this loop, the weight is changed into e to the I 2 e naught pi minus gamma. And now let's imagine I chose e naught such that e naught is gamma over pi. If I do this, this becomes e to the plus I gamma. I've changed the weight of the loops surrounding this point from e to the minus I gamma to the e plus I gamma. Conversely, if the loop were oriented the other way, I would get, it's not a good choice of color. Let's find red. Sure, there's a red somewhere. Conversely, if the loop is oriented the other way, I get a plus e to the I gamma. But now, because the loop is oriented the other way, the height inside has decreased by pi. So now I get this. And instead of the plus I gamma, now I need a minus I gamma. In both cases, what I get is simply the conjugate. But remember, we sum over orientations. So because we sum over orientations, the weight of the loops surrounding the vertex operator in the end is still n. Instead of having once e to the I gamma, the other time e to the minus I gamma, now I have once e to the minus I gamma and once e to the plus I gamma. But because I sum over both, the weight is still n. Then the weight of a loop surrounding 0 is still n, coming now as the sum of the complex conjugates instead of e to the I gamma, e to the minus I gamma. Therefore, this average is equal to 1. It is transparent. Do I make that clear? Yeah, I know I kind of got confused and it sort of stopped the momentum. So the goal is to show that the average of this is equal to 1. And we show it by showing that the partition function is z over z. The partition function is not changed when we insert this operator. And it's not changed because all this operator does is change the weights of the loops that surround it into their complex conjugate. And you may object, oh, but you suppose there was only one loop. But now the argument I can make for every loop surrounding the point. So if I have several loops surrounding the point, for each of these individually, I can make the argument. I can see by how much the height in the center changed. I can see the phase due to the loop surrounding the point, and I can see that the two compensate. As for the loops that don't surround the point, anyway, they don't care because they don't change the values of phi of 0. So for them, phi of 0 is completely transparent. I'm seeing puzzlement. Okay, well, that's the claim. The system is such that average of e to the 2I is 0, phi of 0 is equal to 1. Microscopically. And therefore, we encounter a paradox because we said, oh, in the Coulomb gas, in the free boson, only averages of correlation functions whose charges are 0 vanish. And now the next thing I tell you is, no. I need some system where the average of a vertex operator of very specific charge does not vanish. So what do I do? Well, the only way to solve the problem is to acknowledge that if anything, our system cannot be described by just a naive free boson. Really, the loop model must correspond to a non-neutral free boson, which means that really to calculate critical exponents, we cannot exactly do what we've done so far, which means that non-vanishing two-point functions are not e to the I e phi of 1 e to the minus I e phi of 2. Nope. They are average of e to the I e phi of 1 e to the I 2 e0 minus e phi of 2. This is the first thing we learned. The only quantities we should safely consider when we want to map the loop model to a free boson are quantities such that the total charge, which means the total sum of exponentials when we look at correlation functions of exponentials, should be equal not to 0, like we had, but to 2e0, okay? Which is perfectly easy to construct. What you can do, for instance, in practice, what you can do is, it's not that we are cheating. What we are doing is, if you wish, focusing on a certain sector. So what this means, alternatively, this means we must put what's called a charge at infinity and calculate limit as r goes to infinity of e to the I e1 phi of 1, e to the I e2 phi of 2, e to the minus 2I e naught phi of r over average of e to the minus 2I e naught phi of r, something like this. Okay, and if we send a point very far, then we still have charge, actually, well, yeah, let's keep it as is. Okay, so we want to focus only on configurations where the total charge E1 plus E2 is equal to 2 E0. This is tricky because there may not always be an infinity, yes? Can the loops be thought of as holonomies? Yeah, in a certain sense. I'm not sure it takes us very far, but yes.
So you're not, because you have the vertex operators,
Yeah.
but you're trying to redescribe your theory now in terms of loops.
Yes, yes.
But there is not a map one-to-one, right? It's
between what? Between the loops and
loops and vertex operators.
Well, a loop is a vertex operator is an observable more than a loop, right? I mean, so I'm not sure. I think I see what you. Let me carry on just a tiny bit, and we will see very soon what the question of the one-to-one correspondence comes about. So first of all, we must calculate this thing, And this thing, if you go through the motion, should go like 1 over R2 to the E times E minus 2 E naught over G. Okay, so that generalizes the E1, E2 over G that I had earlier. So that's the first point. The gas is not neutral. It sounds reasonable, but it's extremely hard to understand what it means in practice, and this is why this route eventually fails, as far as I know. We can't calculate 4-point functions using this route. We can calculate critical exponents, but that's pretty much it. It's very hard to make really complete sense of what we want to do when we say we want to have correlators whose total charge is non-zero, especially if we're in a finite volume, like on a torus or something. But at least that's the right direction to think for critical exponents. The second point is that, moreover, the free boson must be compactified. Ouch. What does that mean? Well, it means that in many cases we have to face the fact that our field phi is not uniquely defined. For instance, on a torus, so let me elongate the torus to have a cylinder. I can perfectly well actually, let's draw a real torus for a change. So if now I put my loops in a doubly periodic geometry, okay, I may have loops like these, which are nice, because the field outside phi is well defined. But imagine I had a loop like that one. Then I would encounter now definitely a problem, because my rule is that phi to the left should be equal to phi to the right plus pi. But now when I go around the system along the non-contractible cycle, I have a domain that has phi plus pi on one side and that comes back as being phi on the other side. This is a problem. Phi is not uniquely defined. It's not as horrendous as we may think it is. This is very much like an angle. It is very much like an angle in the classical XY model, where you may have small vectors rotating around the axis as you go around the period, and the angle made by these vectors and the horizontal axis, say, is well defined only up to multiples of 2 pi. It's not the first time we encounter things that are not uniquely defined, but it is definitely a little disturbing, although it's very natural when you think of what's known about the free boson in conformal field theory, but phi really is only defined modulo something. Phi is only well defined modulo, and then you have to be a bit careful. For the Potts model, I have said that repeatedly, the number of loops is even, the number of non-contractible loops is even. So for the Potts model, which is essentially the thing I'm discussing whenever I become more quantitative, for the Potts model you encounter always pairs of loops as you go around the system. So phi is only well defined modulo multiples of 2 pi. If it were for the ON model where you could encounter odd and even number of loops, it would be defined only modulo pi. But in this case, it's defined modulo 2 pi. So for the string theorist among you, it's like a radius equal to 1. Phi is identified with phi plus 2 pi r. The radius is equal to 1. In StatMech, usually we fix the radius, and the different models correspond to different coupling constants G. In conformal field theory literature, very often people do the opposite. They have a fixed normalization for the action, and the dependency of the model on the other parameter comes from the radius. But here, this corresponds to radius r equals 1. So the boson associated with our model is not uniquely defined. There is a quantity we call a charge at infinity or something that makes the system non-neutral. And depending on the geometry, we may have even more perverse effects, because of course, now I can tell you about the third horror. The third annoying feature is that the minute we think about topology, we see that we cannot so easily give non-contractible, give all the loops the weight n, because if now we elongate the torus into a cylinder, a non-contractible loop on the cylinder has as many left as right turns. So it is also difficult to give to these loops the proper weight. We should give them the weight n if the model we want is a genuine loop model where all the loops have weight n, but in this topology it's not possible unless we do something else. So we're also having this difficulty. In fact, you could have pointed out that this business of left minus right turn is equal to a fixed number is true only if we don't have curvature. If we started trying to put our lattice on some curved domain, it wouldn't work anymore. We would have to adjust for the curvature. So definitely the theory that's lurking behind the loop model is not just a free boson. It is something more complicated. It has a charge at infinity. It has a dependency on the curvature, which is more or less the same when you think of it. It is compactified and maybe more. We don't really know what it is, in fact. It's fair to say it's still an open question. That's, again, why the bootstrap strategy is so much more useful, because we don't have to rely on an action anymore. But for now, we're still relying on an action. Okay? So now I'm going to get into these different aspects in slightly more detail. And for now, maybe I would like to finish the identification of, well, E0, G. So far, I haven't really told you what these are, depending on the model. So let's finish with this. So the thing we've seen is that if we take E0 is gamma over pi, we have operators whose average is equal to 1, and therefore we want to study the model with non-zero charge, fine, but we still haven't associated anything with n. So now the question is, how are n and g related? Remember, the parametrization is n is 2 cosine gamma, and gamma belongs to, so if n is square root of q, gamma belongs to pi over 2, 0, but very often I may extend it all the way to 0 pi. So now the next question is, how are n and g related? So there are various strategies to do this. There is one cute argument, which I'm going to give you, even though I don't find it actually so convincing, but the argument will be obtained by saying that if we look at how the discrete solid-on-solid model approaches the free boson, there will be obviously corrections. So the action will be at some intermediate stage in a renormalization group. We should expect that the action will be something like this. There may be term accounting for the charge at the non-zero charge, which I'm not going to write down. No point getting into this right now. But then there may be other terms that could be either irrelevant or marginal. Okay? And imagine we represent these terms. So what kind of terms can we have when we look at the action perturbatively near the Gaussian fixed point? In general, we should expect some vertex operators. So these other terms, I should be able to write in general as some sum of e to the 2I e phi, or sorry, let's write it e to the I e phi. And because phi, after all, is only defined modulo 2 pi, which, by the way, is kind of obvious when you think of how we've defined it recursively. We had to start from somewhere, and depending on that somewhere, we may have a global change of the value of phi by 2 pi. So it's clear that e should be an integer. Okay, so in general, we can expect corrections to go that way. And then, so the argument would go that if we change the value of n and k, the coupling constant, at the same time to remain on the critical manifold, well, we should have some sort of marginal perturbation. So definitely it is natural to look for something marginal in this expansion. So it should be possible from the point of view of this action to have an exactly marginal perturbation, because changing n and k should correspond to a marginal perturbation. If we stay on the critical line, right? So what I mean by this is I have my phase diagram with n and k. I have something like this. If I look at the theory right here, and if I assume the theory is fully described by an action of this type, there should be room for a perturbation, so I could move exactly along this direction, remain critical while changing things slowly. In the renormalization group, it means there should be a marginal operator. Now, of course, there's a marginal operator here, but somehow, this is not the one we want. The claim would be that there is another marginal, potentially another marginal operator, which would be coming from this one. And yes, so that's, I think I may have a factor 2 not correct here. Yeah, well, depends on the model. So, yes. Yeah, that's a bit dumb, but a factor of 2 is going to spoil my life. It's all the question of whether the field is defined by multiples of pi or 2 pi. So, okay, well, so I'm looking for a marginal operator here. Okay, let's do it this way. I'm looking for a marginal operator here, and let me claim that the good operator to think of exponential 2I phi. Okay. not e to the I phi. Okay, so that let me think of this. I'm not sure how I can explain it the best way, but it's not too horrible because we could have e to the I phi as the marginal operator. Well, let's assume it's not the case. Let's assume it's not allowed in the system for some reason, which actually I could explain, but it would take me more time than I want to devote to this. Let me just believe that the marginal operator I need to think of is the one exponential to I phi. So the logic apart from this 1, 2 is quite solid. I'm looking for marginal deformations, and I must acknowledge that these deformations will come either as polynomials in derivatives of phi or exponentials of phi, and I must now believe that it's not the right one, the one with equals 1 is not the right one, but the one with 2 is the right one. If we just believe this for the time being, the point is that now the dimension, so in general I'm going to write the correlation functions of some observables, scalar observables, as 1 over R1, 2. So I write it to the 2D, and D is the dimension of the field. Like I mentioned earlier, I use this notation already. The dimension is equal to, we see, E times E minus 2E naught over 2G. Yes. With E is 2, that's 4 times 1 minus E naught over 2G. Okay? And moreover, and now the dimension of a marginal operator, I said it has to be marginal. A marginal operator is an operator of dimension exactly 2. That's the operator whose eigenvalue in the RG is 0. So if I demand that this is 2, if I demand marginality, I get 1 minus E naught equals G, or E naught is 1 minus G. And that's really very beautiful because, yes, okay, that's fine. That's very nice because finally it gives me the relationship between E naught and G. But E naught was gamma over pi, remember? So if I have gamma, I have E naught. If I have E naught, I have G. If I have G, I have everything. So for the Potts model, we have square root of Q is 2 cosine gamma, which is 2 cosine pi is 0, and G is 1 minus E naught, which is 1 minus gamma over pi. So that's it. For a given Potts, if you believe all this stuff, which I agree is a little bit hard to swallow, if you believe all this stuff, you start from a Potts model, you calculate gamma, from gamma you calculate G, and that's it. You have all your parameters. You have G, you have E naught, and therefore you have the dimensions of the vertex operators. So if gamma is between 0 pi over 2, we get G in between 1/2 and 1. Okay, if we allow formally to gamma to run between 0 and pi, we get G between 0 and 1. Okay. So now in 5 minutes, let me calculate our first critical exponent just for the heck of it. Let's see what kind of prediction we get from this, right? So one prediction which is amusing is let's go back to the question of what is the probability that 2 points belong to the same cluster in the Potts expansion. Okay. How do I make sure in this formulation that 2 points belong to the same cluster? Well, that's easy. I should ensure that the 2 points are not separated by a loop. Remember, loops surround clusters. If I want 2 points to be in the same cluster, means there should be no loop surrounding them. So these loops, I should kill loops surrounding the points. It's, by the way, exactly the same in the Ising model. Remember, we talked about the high temperature expansion of the Ising model. What's the probability that 2 points belong to the same cluster? It is that they don't belong to different clusters, which means there is no cluster boundary separating the two. So how do I find this probability? I must kill the loops surrounding all the points. Well, I'm going to insert here an operator, e to the I e1 phi of 1. And here I'm going to have e to the I e2 phi of 2. And then I have to be very careful. I want to kill the loops surrounding the points. But every time I have a loop surrounding a point, what does it do, this loop? It changes the height inside. In this particular drawing, it changes the height inside from whatever it was to the same height plus pi. Okay? So if E1 minus E2 is equal to plus or minus 1/2, every time I'm going to have a loop separating the point 1 and 2, phi of 1 minus phi of 2 is going to be changed by plus or minus pi, so I'm going to give to these loops a factor that's going to be e to the plus or minus I pi over 2, which sum is 0, so I'm almost killing those loops. But not quite, because they had a weight coming from the angular dependency. So if now I have E1, if I take E1 is E0 plus 1/2, and E2 is E0 minus 1/2, then what do I get? A loop going around gets a weight, here in that case it's e to the minus I gamma. That's the weight it gets from these left terms. Okay, but because of this insertion here, it gets another weight. It gets another weight, e to the I e0 pi. Now e to the 2I e0 pi was killing the e to the minus I gamma, replacing it by an e to the plus I gamma. E to the I e0 pi simply makes this into 1, and the 1/2 gives to this loop the extra factor I. So in the end, the loops surrounding the points, they simply get the weight e to the I pi over 2 if I go in this direction, and e to the minus I pi over 2 if I go in the other direction, which add to 0. Plus, the sum of the two charges is really equal to 2 is 0, which is what I want in order to have a non-zero correlation function in my non-neutral Coulomb gas. So as a result, I get the dimension of the corresponding operator, and that dimension is, I had E times E minus 2 E naught over 2G, which I can take E is E1 and this was for E and 2 E naught minus E, right? So this simply E is E1 plus 1/2. So that's E1 plus 1/2 times minus E1 plus 1/2 over 2G. That's 1 over AG minus E naught square over 2G. That's the dimension. Okay? So 1 over AG minus G minus 1 square over 2G. So if you put the numerical values, I see it's late, I'll probably finish this next time, but let me just quickly go over this. If I take gamma is 1/3, gamma is 1/3 is Q equals 1, so that's G is 2/3. If I replace, I find that this is equal to 5/48. Which corresponds to the fractal dimension of the clusters to be 91/48. That's a very famous result, is the dimension of the fractal infinite cluster at the percolation point, which coincides with the dimension of Ising spin domains in the high temperature Ising model, and that's one example of critical exponent. I'm sorry I went a little bit fast at the end. I will go over this a little bit more later, and then we will move on finally to the full conformal field theory. So thank you for your patience.